sulfuric acid as 2 oxo linkage, 2 hydroxyl group attached to it. Now on one of the oxygen make a peroxy linkage. This will become H2SO5. This is called also called Caro's acid. Okay. This is, in this case you have 2 sulfuric acid unit. This is just the way you can remember it. This is not the way it's formed. This is just should remember. This is just a way to remember it, because you should remember the structure. So in case of peroxo disulfuric acid, so you have 2 sulfuric acid, and between these 2 sulfuric acid you have a oxo linkage. That's how you can remember it. Right? This is also called Marshall's acid. That's its pet name. So what is the oxidation state of sulfur in peroxo monosulfuric acid? It is +6, and it is +6 here as well. But if you calculate it from the formula +1 x and -2, it will turn out to be, which is wrong, because it cannot be more than +6. Similarly, in this case, it will be wrong. So it can only be determined through the structure. So by breaking the bonds, which we have studied earlier as well. Should I raise it? Sulfuric acid is a very important chemical compound. It's usually also called king of acids or king of chemicals, because it has multiple properties. It's a strong acid. It has oxidizing behavior, so it can function as an oxidizing agent, and it can also function as a dehydrating agent. Right? So why it's a strong acid? Because of the high Ka value. So oxygen hydrogen bond can be ionized and can give you, so H2SO4 being a dibasic acid will break down into H plus and HSO4 minus. This is called bisulfate ion. This bisulfate ion will further ionize and will give you SO4 2 minus. The equilibrium constant of the first reaction is called first ionization constant of sulfuric acid, and this is called second ionization constant of the sulfuric acid. So for any polybasic acid, which means any acid which can furnish more than one H plus, H3PO4, H2SO4, any acid which can furnish more than one H plus, they, whenever we're looking at their acidic strength, we actually look at the individual removal of each H plus. So when first H plus comes out, the Kc value is called first ionization constant of the acid. For the second step, it's called second ionization constant of the acid, and so on. For any acid, the Ka2 is lesser than Ka1 and Ka3 is lesser than Ka2. So successive ionization constant of any polybasic acid decreases, because once you have removed an H plus from the molecule, it becomes difficult to remove another H plus from the molecule, because it has become negatively charged. Right? So it will be obviously slightly difficult. So equilibrium constant of such reactions will be lower than the previous one. 0.1. So this is a question which usually comes. So why first ionization constant of sulfuric acid is more than the second ionization constant of sulfuric acid? The same question can be extended to any polybasic acid, right? 0.1. So because of the high value of Ka1 and then Ka2 also, or the cumulative multiplication of the two. So if I have to write this H2SO4 giving 2H plus and SO4 2 minus, so overall ionization constant of the reaction will be K1 into K2, right? So that's what really happens in the case of some polybasic acids, in which if Ka3 and Ka2 are very low, smaller than 1, so it reduces the overall ionization constant of the acid. But in this case, both of them are higher. But first is higher than the second one. Its oxidizing behavior lies with the fact that sulfur is present in the +6 oxidation state, and it can oxidize many compounds, like or many ions, for example. So if I'm reacting Fe2 plus with H2SO4, it will convert it to Fe3 plus. It will convert I minus to I2 and so on. So these sub reactions we can write easily. We just know the basic of it, like this is how what's going to happen. Dehydrating agent. It's a good dehydrating agent. You might have studied this, that if you have, for example, sugar and you make it react with concentrated sulfuric acid, it forms char. Right? Charring of sugar भी बोलते हैं ना इसको, black powder रह जाता है. So why does this happen? Or simple case, this is something which you must have started. For example, I have CH3, CH2, OH, ethanol, and I am making it react with concentrated sulfuric acid. What will happen? Alkene form हो जाएगा. What is the alkene which will be formed here? It will be CH2 double bond CH2. So this has formed by removal of H2O. So this process is nothing but dehydration of alcohol. And how did you conduct the dehydration? Using concentrated sulfuric acid. Okay. One more point which you should remember is that here P2O5, ये हमने पढ़ा है, right? We have studied about P2O5. P2O5 is also a dehydrating agent, and it is also a very powerful dehydrating agent. If I react P2O5 and H2SO4, then in that case P2O5 dehydrates sulfuric acid. So P2O5 is such a powerful dehydrating agent that it can even dehydrate another dehydrating agent, which is sulfuric acid, and can form SO3 from it. Right? So this is something which you should remember. Now, sulfuric acid can be prepared in manufacturing process, which is also called contact process. The process is pretty simple. What you do is you take a sulfide of any compound, or you directly take the sulfur, either sulfur or some sulfide. You oxidize it or heat it in the presence of higher in oxygen at higher temperature, and forms SO2. The SO2 gas is mixed with oxygen gas, and in presence of catalyst, it is converted to SO3 gas. The SO3 gas obtained is made to react with H2SO4 instead of H2O. So what we do is we make it react with H2SO4 and form H2S2O7. This is called oleum, also called fuming sulfuric acid. So the advantage of forming oleum or fuming sulfuric acid is that the transportation of sulfuric acid becomes easier, and removal of SO3 from the chamber is easier, because so this SO3 get absorbed in sulfuric acid like this is a gas, this is a liquid. This gas gets absorbed and form oleum. So in this oleum, if I add calculated amount of water, I'll be able to produce pure sulfuric acid. So the oleum can be treated as a mixture of H2SO4 and SO3. They remain in equilibrium because So next is halogens. So the name of halogens came from the word halos, which means sea salt producer. So fluorine, chlorine, bromine, iodine, and acetine. Acetine is radioactive, so we do not really study its compounds. So these are the four important halogens which we have. While observing their properties, the atomic size increases down the group. Simple prop. Ionization energy decreases down the group. Electronegativity decreases down the group. What are the values? 4, 3.2, 3, 2.7. Approximate values, right? So it decreases down the group. Electron affinity decreases down the group with an exception between fluorine and chlorine. So the order of electron affinity is chlorine, then fluorine, then bromine, and then iodine. Right? Done? Now let's talk about their elemental form. So they exist in the diatomic molecular form F2Cl2, Br2 and I2. So here we have some interesting properties. So in case of the F2 and Cl2, both of them are gases at room temperature. Br2 is a volatile liquid. Can you see if I write in red color? And I2 is volatile solid. Right. Now, so can you just explain why this is gas, this is liquid, and this is solid? So how does that affect? So because of the increase in intermolecular forces of attraction, which is what kind of attraction we'll observe here between similar molecules. So if you have F2 molecule and F2 molecule, what kind of molecule is this F2? Is it a polar molecule or a non-polar molecule? Non-polar. So what kind of force you'll observe between the two? Dispersion forces or London forces, which depend upon the molecular weight. So as molecular weight increases, the intermolecular force of attraction between them increases, and thereby we see the change in their densities and then change in their physical states specifically, which is happening here. Right? Got it? Now, the second interesting property which we observe here is that their color. F2 is yellowish in color. Cl2 is greenish yellow in color. Br2 is reddish brown in color, and I2 is violet in color. So their color is due to the absorption of the electromagnetic radiation, which is light. So what really happens? This is something which I'll explain in detail in coordination compounds. What really happens is that the compounds can absorb light. From the light, which is actually a mixture of multiple kind of radiation, it will absorb some specific radiations, right? Let's just assume that. So F2 is absorbing some specific radiation which is resulting in its yellow color. I2 is absorbing some specific radiation which is resulting in its violet color. So violet and yellow actually go in combination. So it is if it's absorbing violet color, it appears to be yellow. If it's absorbing yellow color, it will appear to be violet. And why it's absorbing violet color and it's absorbing yellow color? Because of the energy gap between the energy states in which electron is jumping. I'll explain this color thing in coordination compound. This is the same theory which we'll study in crystal field theory exactly. Now, so coming to the another property, which is the bond length. and thereby bond strength. What bond length I'm talking about? The bond length between element-element bond, or bond strength of the element-element bond, which is this. So as I can see, fluorine is a small atom, chlorine is a bigger atom, and so on. So bond length should increase down the group, and bond strength should decrease down the group. This is how it should be. But the bond strength of chlorine is better than that of bromine, and which is better than that of fluorine, and which is better than that of iodine. So what really happened with fluorine? I mean, rest of the stuff is there, which should, well, this is how it should be. But fluorine should have been here, but it's present at this position. So if I draw the order of the bond length, it will be reverse of it, which means so bond length is smaller in case of chlorine, then larger in case of bromine, then larger in case of fluorine, and then larger in case of iodine. So this is the order for their bond length, and this is the order for their bond strength. So why do this fluorine has larger bond length and smaller bond strength? So this happens because, again, because of its small size and 3 lone pairs on it. So 2 fluorine atoms, when they overlap their 2p orbitals and form a sigma bond, so this sigma bond has been formed by 2p orbital of one of the fluorine atoms and 2p orbital of another fluorine atoms. ठीक है ना? तो इनका 2p से sigma bond form हुआ है. The 2 fluorine atom has 3 lone pairs around them. So when they'll come close to each other, which they will definitely because of their small size, the repulsion between these lone pairs will be quite high. And to optimize this repulsion, what they'll do is they will increase their bond length so that this repulsion can be optimized. And since they increase their bond length, so the bond strength decreases thereby. So this is an important point from the competitive exam point of view. You should remember this. Another important compounds of halogens are hydrides, which are also called haloacids or also called hydraacids of halogens. HF, HCl, HBr and HI. So if I talk about their property, their acidic strength increases down the group because of increase in bond length. Though if I go in detail, it can be explained thermodynamically as well, but we can remember it simply by the bond length and the electronegativity factor, which we have studied earlier. The second is the reducing behavior. Reducing behavior depends upon ease of removal of hydrogen. So hydrogen can be removed, and what kind of hydrogen I'm talking about? Not H+, but I'm talking about the nascent hydrogen here. So nascent hydrogen can be removed from, most easily can be removed from HI because of the larger bond length. So reducing behavior will increase down the group. So HI is a better reducing agent than HBr, and which is better than HCl and then HF. In fact, if you have seen in many reactions, HI is used as a reducing agent. HBr and HCl are not. So HI has significant reducing behavior, which can be utilized in many reactions. Should I erase it? Oxides of halogen family. So they form acidic oxides, obviously, because they're strongly electronegative elements, they're non-metallic in nature. So fluorine does not form oxides. The compound of oxygen and fluorine, which is O2F2 or OF2, cannot be called as oxide because fluorine is more electronegative than oxygen. So such compounds are called actually fluorides of oxygen instead of oxides of fluorine. So this is so dioxygen difluoride and oxygen monooxygen difluoride. The compounds of chlorine, so chlorine actually is the element which forms most of the oxides like Cl2O, ClO2, Cl2O7, etc. And similar thing happens with bromine and iodine. So all of the oxides are acidic in nature. The next is oxoacids. This is important. So halogens show 4 kinds of oxoacids: HOX, HOXO, HOXO2, and HOXO3. This can be also seem to be written like HXO, HXO2 in just simple molecular form, HXO3 and HXO4. So X represents here halogens: fluorine, chlorine, bromine and iodine, right? So this one is called hypohalous acid. This one is called halous acid. This one is called halic acid, and the last one is called perhalic acid. Right? The oxidation state of halogen in hypohalous is +1. It's +3 in halous. It's +5 in halic and +7 in perhalic acid. Right? If I talk about the structure of these oxoacids of halogens, so hypohalous acid is of this kind, HOX. The halous acid is of the different kind. This is X double bond O, OH. This is X double bond O, and then OH. This is X double bond O, double bond O, double bond O, and then OH. So the hypohalous acid does not have oxy linkage, as in like the double bond O kind of linkage, but the others have. In these cases, this hydrogen is acidic in nature, the hydrogen bonded to the oxygen atom. So important point which should be remembered is here is that all of them are monobasic. So each molecule can release only one proton, right? So all of them are monobasic. This is one point. Second point to be remembered here is that as you can see, oxidation state increases, the acidic strength increases. So if I have, for example, 4 oxoacids, HClO, HClO2, HClO3 and HClO4. So which one will be the most acidic amongst all? HClO4. So as the oxidation state of the central element of the oxoacid increases, the acidic strength of the oxoacid increases, except in case of phosphorus. Like see, this is the case which is there in case of H2SO3, H2SO4. Similarly, it happens in case of HNO2 and HNO3. This was a doubt also. So nitric acid is more stronger than nitrous acid. I'll explain it here. Got it? Let's just quickly understand what is the reason behind it. The reason behind it is very simple. See, the halogens there, let's just assume this halogen to be chlorine in all the cases. So I'm just redrawing this structure. So this is chlorine, oxygen, and hydrogen. Okay? Now, so if I observe all the 4 oxoacids of chlorine, So there is a polarity in the bond of oxygen and chlorine, which will result in the removal of H plus easily from this bond. So same thing is happening here. But what is different in all the cases is that the atom to which oxygen is bonded to. But you'll say, no, it's same. It's chlorine, 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 and chlorine. That's same. But the state of chlorine in all four acids is different. Here, this chlorine is not bonded to any other oxygen atom. This chlorine is bonded to one oxygen atom. This chlorine is bonded to two oxygen atoms. And this chlorine is bonded to three oxygen atoms. As we know, oxygen is more electronegative than chlorine. These oxygen will pull electron from chlorine. And they will pull more, they'll pull further more. So this chlorine will be the most electron deficient chlorine. This will be less, this will be further less, and this will be furthermore less electronegative. No, I just say it reverse. So electron deficient. So this will be the most electron deficient chlorine. This will be less electron deficient. This will be further less electron deficient, and this will be less electron deficient in comparison to all four. Now, the atom which is by default have electronegative nature. Chlorine is highly electronegative atom, and at the same time this is highly electron deficient. It's something like someone which has strong appetite or very heavy appetite, like have food in large quantity, is asked to remain hungry for a long time. What would be the behavior of such a person, right? So this is kind of the state will be the case with the chlorine. So this is a highly electronegative atom, and at the same time this is highly electron deficient. So because of this state, this chlorine will start pulling electron from this bond, or I can say that this will resist to give its electron to oxygen. Now oxygen wants to manage its electron density around it. So, and it cannot do anything to the chlorine because it knows it's right now in a very pissed off situation. It's great not to talk to him and actually distribute the load to hydrogen. So you can remember it in a simple terms. Whenever you have an element bonded to oxygen, which is and then bonded to hydrogen, the more this element will be, more will be the polarity in this bond, and easier will be the removal of hydrogen. Lesser is the electronegativity of this element, lesser will be the polarity here, and lesser will be the ease of removal of hydrogen. So this is a very incremental differences which we are observing here. Definitely all of them are good acids. But if I want to compare them, since this chlorine will be highly electron deficient, and or I can say that will be highly electronegative. No, we could not get this point. So electronegativity of an element does not remain constant throughout the lifetime of the element, right? So electronegativity of an element changes with its hybridization, it changes with its oxidation state. Higher the oxidation state of any element, higher will be its electronegativity, because the high oxidation state represents high electron deficiency. If it's more electron deficient, it will have high tendency to pull electron from the sigma bond. So it means that this chlorine will be highly electronegative, possibly more than oxygen. This chlorine will also be highly electronegative, but lesser than this because lesser oxidation state. This chlorine will be highly electronegative than normal chlorine atom, but lesser than this one because of lower oxidation state, and so on. So higher the electronegativity of the atom bonded to oxygen, higher will be the acidic strength, and that is the reason why they are strongly acidic. The same reason applies to oxo acids of sulfur. H2SO3 is less acidic than H2SO4. The same reason applies to oxo acids of nitrogen. HNO2 is less acidic than HNO3. The same logic can be applied to similar kind of oxo acids of group members like HClO4, HBrO4, and HiO4. So I have perhalic acid of chlorine, bromine, and iodine. So in this case, all of them are in +7 oxidation state. So what all you have to do is you have to look for the element which is more electronegative, and in the same oxidation state it will be obviously more electronegative. So this is stronger than this one. So can I say that HClO4 is the strongest acid? And it is. So perchloric acid is the strongest acid. Okay, another point which you should remember in this case is the oxidation state wala. There is one exception to it which you should remember, and it's a part of the syllabus also. The exception is lies with the phosphorus, oxoacids of phosphorus, H3PO2, H3PO3 and H3PO4. Phosphorus is in +1, it's in +3 and it's +5. So ideally it should be this, but it follows this order. So this difference in the reverse case is actually not because of the oxidation state, but because of something different reason altogether. That is because of their structure. In these three cases, what happens is that not all hydrogens are attached to oxygen atom. In H3PO4, 3 hydrogens are attached to 3 oxygen atom. In H3PO3, 2 hydrogens are attached to oxygen atom, but 1 hydrogen is attached to phosphorus directly. In this case, only 1 hydrogen is attached to oxygen and 2 are not attached to phosphorus. Because of this difference in their structure, their successive ionization constants Ka1, Ka2, Ka3 will change. This will only have 1 Ka. This will have Ka1, Ka2, ये monobasic है, dibasic है, and this is tribasic. So this will have K1, K2, K3. K2 and K3 are pretty low values, lesser than 1. So their overall dissociation constant will be lower than the other ones. Got it? Should I erase it? Okay. Another important property, another important thing which you should remember in this case is that we had 4 kinds of oxoacids: HOX, HOXO, HOXO2 and HOXO3. Halous as hypohalous, halous, halic and perhalic. And you might have seen, like, I mean, us is used with the lower oxidation state, IC is used with the higher one. So halous, halic, perhalic, higher than this one, hypohalous, lower than this is how you can remember. Now, second thing which you should remember is that fluorine, chlorine, bromine, iodine, these are the 4 halogens I am studying. Fluorine only forms HOX and does not form these. Why? Because to form HOXO, fluorine need to form 3 bonds with oxygen. Can it form 3 bonds with oxygen? It cannot. Can it form 5 bonds, 7 bonds? Not at all. So these compounds cannot be formed. Chlorine is the one which forms all of them. Bromine forms these 3, not this one. Iodine forms these 3 and not this one. Because so they form this one, but that is not very stable. So just remember these 3, that they are not formed, and these 2, and definitely rest all the column, all these sections will be filled. So we had a doubt. So we had 3 doubts. One is the strongest acid, which we have discussed. HClO4 is the strongest acid. What is the oxidation state of oxygen in HOF? So as I can see, this is the structure of the molecule. In this case, if I calculate the oxidation state of oxygen by the heterolytic bond cleavage, if I'll break this, will be -1 and +1. This will be +1 and -1. So it will be 0. Right. The third question is, which one is more acidic from HNO2 and HNO3 and why? This is something which we have discussed because of the higher oxidation state of nitrogen, it being more electronegative. So as you can see, structure of nitric acid is this, and structure of nitrous acid is, so both have this similar structure, NOH, NOH. Here nitrogen is bonded to oxygen atom, having +5 oxidation state, will be more deficient, will be more electronegative, and thereby will ease the removal of H plus from here. This nitrogen is in lower oxidation state, this is in higher oxidation state. So this is in lower oxidation state will be less electronegative, will pull this electron less, and thereby this H plus will not be removed so easily as in case of HNO3. So that's why HNO3 is more acidic than HNO2. In halogens, the another important thing is interhalogen compounds. So what are interhalogen compounds? The compounds which are formed by two or more than two different halogen atoms. But as we have observed and have tried to form these compounds, we have realized that we cannot form compounds with more than two different halogens. Even if we try and form them, they converts back to the compounds of the respective compounds which are formed by two different halogens. So compound three different halogen means like I'm forming a compound with fluorine, chlorine and bromine, all three. This is what I'm talking about. Four different halogen means I'm talking about a compound which is formed by, for example, Fx, Cl, some Br, Z, Niw. So such compounds cannot be formed easily, even if we try to try different halogen compounds we have tried to form. They have been processed, but they quickly breaks down and forms the interhalogen compounds of the category in which you have only two different types of halogen atoms. So we represent it by XX dash. So X represents one kind of halogen, X dash is another halogen. So they are usually like XX dash, XX dash 3, XX dash 5 and XX dash 7. This is dependent on their oxidation state range, which is from, what is the range of oxidation state of halogens? What is the range? -1 to +7. Right? And this is except fluorine, because in fluorine, the oxidation state can only be either -1 or 0. Right? In any of its compound, it will always be -1. In its pure form, it will be 0. That's it. But for other halogens, it will be -1 to +7. In most of the compound, it's -1. But we are studying actually there are compounds which are not really common, like the less common ones. In such cases, it is +1, maybe +3, +5, and the +7. So the one which is in the higher number is the one which is more electronegative. So electronegativity of X dash is higher than the electronegativity of X. Like for example, IF, IF3, IF5 and IF7. Got it? So, okay, I think our time is over. So we'll resume right from the interhalogen compounds in our next lecture, and we'll start with the coordination compounds. So we're left with very small portion. So we just quickly discuss the interhalogen compounds, and then we'll study some compounds of and properties of the noble gases. Suppose that we'll be starting with the coordination compounds. So just like just have a look at the topic from the NCERT before you come for the next class. Thank you.